I wouldn't surprise you by saying that science is intimately connected to our real lives. Hey, everybody! As you have already realized, today we are going to look at 20 phenomena from the field of physics and their impact on our real life. If you're ready, here we go. Let's start with obvious things. Friction is the resistance to motion when one object moves relative to another. It's a force that we experience every day, often without realizing it. Here's some examples of friction in our lives. Walking. Friction between your shoes and the ground prevents you from slipping. Braking. The friction between brake pads and a car's rotors brings a vehicle to a stop. Writing. Friction between the pen tip and paper allows you to create marks. Lighting a match. The friction created by striking the match head ignites it. Driving. Friction between the tires and the road enables a car to accelerate, turn, and brake. Holding objects. Friction between your hands and objects allows you to grip them. Machinery. Friction is both beneficial and problematic in machinery. It can cause wear and tear, but it's also essential for many processes. By the way, it was some types of friction. Let's explore them. Static friction. This is the force that prevents an object from moving when a force is applied to it. For example, the friction between a parked car and the road. Kinetic friction. This is the force that opposes the motion of an object already in motion. For instance, the friction between a sliding box and the floor. Rolling friction. This occurs when an object rolls over a surface, like a car tire on the road. It's generally less than sliding friction. While friction is essential for many everyday activities, it can also be a nuisance. Engineers often work to reduce friction in machines to improve efficiency, but in other cases, they aim to increase friction for safety or performance. Gravity is a natural phenomenon by which all things with mass are attracted to one another. It's what keeps our feet firmly planted on the ground and the moon orbiting the Earth. Let's look at examples of gravity from our lives. Weight. The force we feel pulling us downwards is gravity. Objects falling. When you drop something, gravity pulls it towards the Earth. Tides. The gravitational pull of the moon and sun causes ocean tides. Orbiting bodies. Gravity keeps planets in orbit around the sun and moons around planets. Space travel. Understanding gravity is crucial for space missions, from launching rockets to navigating spacecraft. Of course, we can't fail to mention the effect of gravity on the universe. Here's some examples. Black holes. These are regions of space-time with such strong gravity that nothing, not even light, can escape. Galaxy formation. Gravity plays a crucial role in the formation and evolution of galaxies. While we often take gravity for granted, it's a fundamental force that shapes our world and the universe. Pressure is defined as the force exerted per unit area. In simpler terms, it's how much force is applied over a specific surface. So, where can we encounter pressure in our daily lives? Atmospheric pressure. The weight of the air above us creates atmospheric pressure. It's what allows us to drink with a straw and keeps our bodies from exploding. Water pressure. As you dive deeper into a pool, the pressure of the water increases. This is why your ears pop. Tire pressure. Car tires are inflated to a specific pressure to support the car's weight and provide traction. Blood pressure. The force of your blood pushing against artery walls is blood pressure. Cooking. Pressure cookers use increased pressure to cook food faster. Hydraulic systems. From car brakes to construction equipment, hydraulic systems rely on pressure to generate force. The same force applied over a smaller area creates more pressure. This is why a sharp knife cuts better than a dull one. As you go deeper into a liquid, such as water, the pressure increases due to the weight of the liquid on top. Pressure is a fundamental concept in physics with countless applications in our daily lives. From the air we breathe to the machines we use, pressure is always at work. A lever is a simple machine consisting of a rigid beam or bar that pivots around a fixed point called a fulcrum. It is one of the most basic tools used by humans to multiply force. Levers operate on the principle of mechanical advantage. By applying a force, effort, to one end of the lever, you can magnify the force at the other end, load. There are 3 types of levers based on the positions of the fulcrum, effort, and load. First-class lever. The fulcrum is located between the effort and the load. Examples: seesaw, crowbar, scissors. Second-class lever. The load is between the fulcrum and the effort. Examples: wheelbarrow, nutcracker, bottle opener. Third-class lever. The effort is applied between the fulcrum and the load. Examples: tweezers, fishing rod, human arm. Levers are everywhere around us. From simple tools to complex machinery, they make our lives easier. Here are some examples. Household items, pliers, can openers, and nail clippers are all types of levers. Tools, shovels, hammers, and screwdrivers incorporate lever principles. Machines, cranes, car jacks, and even bicycles utilize levers for mechanical advantage. Human body, our bones act as levers, with joints as fulcrums, allowing us to perform various tasks. By understanding the concept of levers, we can appreciate the ingenuity behind many everyday tools and machines. Optics is the branch of physics concerned with the behavior and properties of light, including its interactions with matter and the construction of instruments that use or detect light. Light, as we know it, is a form of electromagnetic radiation. It travels in waves, and its behavior can be described by principles such as reflection, refraction, diffraction, and interference. Reflection. This is when light bounces off a surface. Mirrors use reflection to produce images. Refraction. This is the bending of light as it passes from one medium to another, like from air to water. Lenses in glasses or cameras use refraction to focus light. Diffraction. This is the bending of light around obstacles or through openings, creating interference patterns. This is the principle behind holograms and CDs. Optics is everywhere around us. Here are some examples. Vision. Our eyes use lenses to focus light on the retina, allowing us to see the world. Cameras. Cameras capture images by using lenses to focus light onto a sensor. Microscopes and telescopes. These instruments use lenses to magnify or reduce the size of objects, allowing us to see the very small or very distant. Lasers. These devices produce intense beams of light with specific properties, used in everything from barcode scanners to medical surgery. Fiber optics. This technology uses light to transmit information over long distances, forming the backbone of the internet. Optics is a fundamental part of our technological world, and its principles continue to be explored and applied in new and innovative ways. Electricity is a form of energy resulting from the movement of electrons. It's a fundamental force that underpins modern life. How it works. At its core, electricity involves the flow of electrons through a conductor. This flow, called electric current, is generated by a potential difference or voltage. Let's see some examples of electricity in our lives. Lighting. From incandescent bulbs to LEDs, electricity illuminates our homes, streets, and workplaces. Heating and cooling. Electric heaters, air conditioners, and ovens rely on electricity to regulate temperature. Communication. Telephones, computers, and the internet all depend on electrical signals for communication. Transportation. Electric vehicles, trams, and trains use electricity for propulsion. Household appliances, refrigerators, washing machines, and microwaves are powered by electricity. Industries. Electricity drives machinery, powering factories and production processes. To meet the massive demand for electricity, various methods are employed. Fossil fuels, burning coal, oil, and natural gas to generate heat, which is converted into electricity. Nuclear power, using nuclear fission to produce heat, which is then converted into electricity. Renewable energy, harnessing energy from the sun, wind, water, and Earth's heat to generate electricity. Electricity is an essential part of our daily lives, powering everything from basic necessities to advanced technologies. Its efficient generation, transmission, and distribution are crucial for modern society. Magnetism is a force that causes certain materials to attract or repel each other. It's generated by moving electric charges. How can we encounter magnetism in our lives? Compasses. These rely on the Earth's magnetic field to indicate direction. Refrigerator magnets. These use magnetic force to adhere to metal surfaces. Electric motors convert electrical energy into mechanical energy using magnetic fields. Generators convert mechanical energy into electrical energy using magnetic fields. Hard drives store data by magnetizing tiny particles on a disk. MRI machines use powerful magnets to create images of the human body. Speakers convert electrical signals into sound waves using magnets. It would be a huge mistake not to mention the magnetic fields. There are invisible areas around a magnet where the magnetic force acts. They have a direction and strength. The Earth itself generates a magnetic field, which is why compasses work. Thermodynamics is the branch of physics that deals with heat, work, and energy. It's the science behind how things get hot or cold, and how energy is transformed from one form to another. Let's explore some examples of thermodynamics in our life. Heating and cooling. From your home's air conditioner to a boiling pot of water, thermodynamics explains how heat is transferred and controlled. Engines. Whether it's a car engine or a jet engine, thermodynamics is the foundation for converting fuel into motion. Refrigerators. These appliances use thermodynamics to extract heat from the inside and release it outside, keeping your food cold. Power plants. Generating electricity involves converting heat energy into mechanical energy and then into electrical energy, all governed by thermodynamic principles. Cooking. Understanding how heat transfers through different materials is crucial for baking, grilling, or boiling. Weather. Atmospheric processes, like the formation of clouds or storms, are influenced by thermodynamic principles. Key concepts in thermodynamics. Temperature, a measure of the average kinetic energy of particles in a system. Heat, the transfer of energy from a hotter object to a colder one. Work, the energy transferred by a force acting through a distance. Entropy, a measure of the disorder or randomness of a system. Thermodynamics is a fundamental science that underlies many aspects of our daily lives. From the way we cook our food to the technology that powers our world, thermodynamics is always at work. Sound waves are vibrations that travel through a medium, such as air, water, or solid materials. When something vibrates, it creates disturbances in the surrounding medium, which propagate as waves. How does sound work? Vibration. The source of all sound is a vibrating object. This vibration creates pressure waves that move outward. Medium. Sound needs a medium to travel. It can't propagate in a vacuum. Human ear. Our ears are designed to detect these vibrations and convert them into electrical signals that our brain interprets as sound. Sound is everywhere in our lives. Here are some examples. Music. Musical instruments create sound waves that we perceive as melodies and harmonies. Speech. The human voice produces sound waves that allow us to communicate. Echolocation. Animals like bats and dolphins use sound waves to navigate and find prey. Sonar. This technology uses sound waves to detect objects underwater. Ultrasound. Used in medical imaging to visualize internal organs. Understanding sound waves is essential in fields like music, acoustics, and communication. Buoyancy is the upward force exerted by a fluid, liquid, or gas that opposes the weight of an immersed object. It's what determines whether something floats or sinks. When an object is placed in a fluid, it displaces a certain volume of that fluid. The buoyant force acting on the object is equal to the weight of the fluid displaced. If the object weighs less than the displaced fluid, it floats. If the object weighs more than the displaced fluid, it sinks. Of course, buoyancy has been in our lives. Ships and boats. These vessels are designed to displace a volume of water equal to their weight, allowing them to float. Submarines. By controlling their buoyancy, submarines can dive and surface. Hot air balloons. The heated air inside the balloon is less dense than the surrounding air, creating an upward buoyant force. Swimming. Our bodies are less dense than water, allowing us to float. Icebergs. Only a small portion of an iceberg is visible above water due to its lower density compared to seawater. Buoyancy is a fundamental principle in physics with numerous applications in our daily lives and in various industries. Inertia is the property of matter by which it continues in its existing state of rest or uniform motion in a straight line unless that state is changed by an external force. It's essentially an object's resistance to change in its motion. Some examples of inertia in everyday life. Car safety. Seatbelts are crucial because when a car suddenly stops, your body tends to continue moving forward due to inertia. Headrests. These prevent whiplash by supporting your head when the car is hit from behind. Spilling drinks. When a car turns sharply, the drink in your cup tends to keep moving in a straight line due to inertia, causing it to spill. Objects at rest. A stationary object, like a book on a table, tends to stay at rest unless a force, such as picking it up, acts upon it. Objects in motion. A moving object, like a rolling ball, tends to keep moving in a straight line unless a force, like friction, stops it. Inertia is directly related to an object's mass. The more massive an object, the greater its inertia, and the harder it is to change its state of motion. Acceleration is the rate at which an object changes its velocity. It can involve a change in speed, direction, or both. Examples of acceleration in everyday life. Car acceleration. When you press the gas pedal, your car accelerates, increasing its speed. Deceleration. When you hit the brake, your car slows down, decreasing its speed. This is actually negative acceleration. Traffic circle. Even if an object is traveling at a constant speed, if it changes direction, for example, the car goes around a corner, it accelerates. Falling objects. Objects falling to Earth are accelerated by gravity. Roller coaster. The thrill of a roller coaster is largely due to acceleration and deceleration. It is important to note a few points. Positive acceleration, when an object is speeding up. Negative acceleration, when an object is slowing down, also called deceleration. Centripetal acceleration, when an object is moving in a circular path. Acceleration is a vector quantity, meaning it has both magnitude, how fast the velocity changes, and direction. Momentum is a measure of an object's mass and velocity. It's essentially the oomph an object has. Here are some examples of momentum in everyday life. Car crashes. The severity of a car crash is influenced by the momentum of the vehicles involved. Larger, faster cars have greater momentum. Sports. In sports like baseball or football, the momentum of a ball or player is crucial. A fast-moving baseball has more momentum than a slow-moving one. Rocket launches. Rockets build up immense momentum to escape Earth's gravity. Collisions. When objects collide, their momentum is transferred between them. Walking and running. Your body has momentum as you move. Stopping suddenly can be challenging due to this momentum. A fundamental principle in physics is the conservation of momentum. This means that the total momentum of a system remains constant unless acted upon by an external force. For example, when two billiard balls collide, the total momentum before and after the collision is the same. Understanding momentum is essential in various fields, from engineering to sports science. It helps us analyze and predict the behavior of objects in motion. Energy conservation is a fundamental principle in physics, stating that energy cannot be created or destroyed. It can only be transformed from one form to another. Let's look at a few examples. Pendulum. A swinging pendulum demonstrates energy conservation. At its highest point, it has potential energy, stored energy, which is converted into kinetic energy, energy of motion, as it swings downward. Roller coaster. At the top of a hill, a roller coaster car has potential energy. As it descends, this potential energy is converted into kinetic energy. Light bulb. Electrical energy is converted into light and heat energy when a light bulb is turned on. Bouncing ball. A ball bouncing on the ground illustrates the conversion between kinetic and potential energy. Car engine. Chemical energy in gasoline is transformed into heat energy, then into mechanical energy to power the car. Understanding energy conservation is crucial for various reasons. Efficiency. By understanding how energy transforms, we can design more efficient machines and processes. Sustainability. Conserving energy helps reduce our reliance on non-renewable resources. Environmental impact. Efficient energy use helps minimize pollution and greenhouse gas emissions. Cost savings. Using energy wisely can lead to lower utility bills. From the simple act of turning off lights to complex engineering designs, energy conservation is a vital part of our lives. Semiconductors are materials that can conduct electricity under certain conditions, but not as well as conductors, like copper, or insulators, like rubber. This unique property makes them indispensable in modern electronics. Semiconductors are typically made from elements like silicon and germanium. By introducing impurities, called doping, into their structure, their electrical conductivity can be precisely controlled. This allows for the creation of electronic components like transistors, diodes, and integrated circuits. Semiconductors are the backbone of the digital revolution. Here are some examples of their applications. Computers and smartphones. The microprocessors and memory chips that power these devices are made from semiconductors. Electronics. TVs, radios, and other electronic gadgets rely heavily on semiconductors. Automotive industry. Modern cars are filled with semiconductors, controlling everything from engine performance to safety features. Healthcare, medical equipment, such as MRI machines and pacemakers, utilize semiconductors. Communication. Semiconductors are essential for smartphones, internet routers, and satellite communication. Renewable energy. Solar panels and wind turbines use semiconductor-based technology to generate electricity. In essence, semiconductors have transformed our world, enabling the development of countless technologies that have revolutionized how we live, work, and communicate. Lasers are devices that produce a concentrated beam of light through a process called stimulated emission. Unlike ordinary light sources, which emit photons randomly, lasers emit photons that are all in phase, resulting in a coherent beam. So, how it works? Stimulated emission. This is the core principle of laser operation. Excited atoms are stimulated to emit photons with the same properties as an incoming photon, creating a cascade effect. Optical cavity. A laser consists of an optical cavity with mirrors at each end. Light bounces back and forth between the mirrors, amplifying the beam. Laser medium. The material used to produce the laser light is called the laser medium. It can be a solid, liquid, gas, or semiconductor. What about lasers in our lives? Communication. Fiber optic cables use laser light to transmit data at high speeds. Medicine. Lasers are used in surgery, eye correction, and various diagnostic procedures. Industry. Laser cutting and welding are precise and efficient processes. Barcode scanners. These use laser light to read product information. Entertainment. Laser shows and laser pointers are popular forms of entertainment. Science. Lasers are used in research, from studying atoms to measuring distances. The unique properties of laser light, such as its high intensity, coherence, and directionality, make it an invaluable tool in modern technology. Nuclear energy is generated by harnessing the energy released during nuclear reactions. This energy, in the form of heat, is used to produce steam, which drives turbines to generate electricity. How nuclear energy works. Fission. Most nuclear power plants use nuclear fission, where the nucleus of an atom is split into smaller parts, releasing energy. Fusion. While still experimental, nuclear fusion involves combining lighter atomic nuclei into heavier ones, releasing vast amounts of energy. Where we can meet with nuclear energy in our lives. Electricity generation. Nuclear power plants provide a significant portion of the world's electricity, offering a reliable and low-carbon energy source. Medical isotopes. Nuclear technology is used to produce isotopes for medical diagnosis and treatment. Space exploration. Nuclear power is used to propel spacecraft and provide energy for onboard systems. Research. Nuclear reactors are used in scientific research to study the properties of matter and energy. Nuclear energy remains a significant part of the global energy mix, and ongoing research is focused on developing safer and more efficient nuclear technologies. Quantum mechanics is the branch of physics that deals with the behavior of matter and energy at the atomic and subatomic level. It's a realm where the familiar rules of classical physics break down and strange and counterintuitive phenomena occur. While quantum mechanics might seem abstract and distant from our everyday lives, it underpins many of the technologies we use. Transistors. The building blocks of computers rely on quantum mechanical principles to function. Lasers. These devices, used in everything from barcode scanners to medical surgery, operate based on quantum physics. LEDs. These energy-efficient light sources leverage quantum mechanics for their operation. MRI machines. Medical imaging techniques like MRI rely on quantum phenomena to produce detailed images of the human body. Global Positioning System. GPS atomic clocks, which are crucial for GPS accuracy, operate based on quantum principles. Quantum mechanics introduces concepts that challenge our intuition. Here are some of them. Superposition. Particles can exist in multiple states simultaneously until measured. Entanglement. Particles can be linked together, sharing information instantaneously regardless of distance. Quantum tunneling. Particles can pass through barriers that would be impenetrable according to classical physics. While these concepts might seem bizarre, they are fundamental to understanding the world at the smallest scales. Relativity is a theory in physics that describes the relationship between space and time and how gravity affects them. It's divided into two main parts: special relativity and general relativity. This theory deals with objects moving at constant speeds in a straight line. The key postulate is that the speed of light is constant for all observers, regardless of their own motion. This leads to some counterintuitive consequences. Time dilation. Time passes slower for objects moving at high speeds relative to an observer. This means that a clock on a spaceship moving at near-light speed would tick slower than a clock on Earth. Length contraction. Objects moving at high speeds appear shorter in the direction of motion. This theory extends special relativity by incorporating gravity. It describes gravity not as a force, but as a curvature of spacetime caused by mass and energy. GPS, the global positioning system, relies on relativistic corrections to provide accurate positioning. Black holes. Extremely dense objects with such strong gravity that nothing, not even light, can escape. Gravitational lensing, the bending of light by massive objects, like stars or galaxies, acting as a lens. While these concepts might seem abstract, they have real-world applications in fields like astronomy, physics, and technology. That's all for today. This video is just a small part of how physics is intimately woven into our lives. There will definitely be a sequel, so don't forget to subscribe. That way you won't miss the next video. See you soon.